All right, it's 8 p.m. Let's begin. Okay, so welcome everyone. Today's crash course is on rate of reactions. So before I start, I just want everyone to know that this is a safe place where everyone can learn from each other. So we have a chat, right? The in-call messages. Okay, so you may ask questions here or you may answer questions here during the crash course. Okay, so it'll be a bit interactive. So maybe when I ask question, then you can send your answers inside the in-call messages. Okay. All right, if not, without further ado, let's begin. Okay, let's look at the agenda. So today we're going to go through two important things. Okay, one is collision theory, and then the other one is the factors affecting rate of reaction. Okay, so factors affecting rate of reaction, there are 5 factors, and all these 5 factors we'll go through in detail. Okay, so these two we'll go through in detail. Then as I'm going through, I'll also go through some questions, right? So the reason why I ask you guys to do the questions beforehand is so that when I go through, you'll understand like, oh, this is what I'm missing, or this is the mistake that I make. Okay, so I'll go through the question, and if you have done them in advance, that is where you'll learn the most. You'll learn what you are missing out on, or what are your mistakes. Okay, then as usual at the end, we'll have a Kahoot quiz, and I'll share more about our class details and also a feedback form. Okay, so the feedback form is for me to improve as a teacher. Okay, and I'm doing all these crash courses for free, right? So all I ask in return is for you guys to fill up this feedback form. Okay, all right. If not, let's get started. Okay, so collision theory, right? First thing you need to know is the collision is for what? It's for your particles. Okay. So for collision theory is basically what needs to happen in order for a chemical reaction to take place. Okay, in total, there are 2 concepts. There are 2 criteria that has to be checked. Okay, so if you don't meet any of these criteria, a chemical reaction will not happen. Okay, so what are the 2 concepts? First one, your reacting particles must collide with each other. Okay, what does it mean by collide? So for example, particles A and B are. We all know that particles, they move in constant and random motion, right? That's the kinetic particle theory. Okay, so when they move randomly, then they suddenly move towards each other. And then they touch each other. This is a collision. Okay, so that is the first criteria. Your particle A and B have to collide with each other. Okay, that's the first criteria. The second criteria of the collision theory is that they have to collide with enough energy. Okay, and what is this energy? Your activation energy. Okay, activation energy is the minimum energy you need to start a reaction. Okay, it's the minimum energy you need to start a reaction. So let me give you an example, right? If your activation energy is 500 kilojoules, okay, kJ is kilojoules. Let's say this is your activation energy. Okay, so if I don't hit 500 kilojoules, right, then a reaction will not happen. So let me draw 2 examples. Your first example, right, A and B. Okay, maybe I name this 1 and 2. Okay, then they collide with each other. And then when they collide, they collide with 400 kilojoules of energy. Okay, then second example, let me use green. Okay, particles 3 and 4. Okay, when they collide with 600 kilojoules of energy. Okay, so for particles 1 and 2, right, will there be a chemical reaction between these 2? Okay, yes or no? Will there be a reaction? I want you guys to comment down below. Tell me in the in-call messages, will there be a reaction for particles 1 and 2? Okay, take note that the activation energy is 500 kilojoules. Okay, come on, guys. Yes, no, okay. Good. Okay, there will be no, okay, good. Most of you say no. So there will be no reaction because they collide with 400 kilojoules of energy only. Okay, 400, of course, is lesser than 500. So if If it's lesser than the activation energy, there will be no reaction. Okay, now let's look at particles 3 and 4. Okay, yes or no? Okay, now I want to ask you guys again. For particles 3 and 4, they collide with 600 kilojoules of energy. Will there be a reaction? Okay, yes. Okay, YW, Faith, both say yes. Good. Okay, because 600 kilojoules of energy is more than 500. Yes, sir, yes. Okay, 600 is more than 500. So it surpassed the activation energy. It already met the activation energy. So yes, there will be a reaction between these two particles. Okay, so now for particles 1 and 2, right, there is no reaction. So what do we call this collision? We call this ineffective collision. Okay, so when your particles collide and they don't meet the activation energy, you call this an ineffective collision. Okay, so what will happen? They'll just bounce off each other. Nothing will happen to them. But if you meet the activation energy, right, we call this an effective collision. Okay, an effective collision is what causes chemical reaction. Okay, so as long as I collide, right, as long as my particles collide with 500 kilojoules of energy or above, there will be a reaction. Okay, there will be a chemical reaction. So now that we understand that, right, this topic is on rate of reaction. So how can we increase the rate of a chemical reaction based on what we just learned? We need more effective collisions, right? Because effective collisions is what causes your chemical reaction. So if I want the chemical reaction to happen faster, I need more effective collisions, okay? So we have to learn this relationship. The higher the frequency of effective collisions, the faster the rate of reaction. Okay, is directly proportional. So I have more effective collisions, the rate of reaction will be faster. Okay, so that is collision theory. Make sure that you understand these two concepts. One, they must collide. Second, they must collide with enough energy. Okay, then if you want to increase the rate of reaction, you must have higher frequency of effective collisions. Okay, now let's move on. Okay, don't worry if you cannot copy this. I will send this PDF with all my inkings in the Telegram channel. Okay. Okay, next, factors affecting rate of reaction. Let's start with the first one. Okay, concentration. So for concentration, right, it's only for solution. Because what is the meaning of concentration? Is the amount of solute in a given volume of solvent. Okay, concentration is the amount of solute in a given volume of solvent. Your solute is the substance that dissolves. Okay, your solvent is the substance that dissolves the solute. For example, you mix sugar and water together, sugar will dissolve, right? So sugar is the solute, water is the solvent. Okay, so it's basically like solute over solvent. So if I have more solute in the same amount of solvent, that means my concentration increase. Okay, or I have less solvent in the same amount of solute, then my concentration increase also. So let's see how concentration affects rate of reaction. Okay, I'll give you a simple analogy. Think of your MRT, right? This is a non-peak hour. Non-peak hour, there's very few people in the MRT. Okay. And then peak hour I draw in blue. So think about like maybe when you end school at 6 p.m. sometimes, then your MRT is very crowded, right? Firstly, all the seats are taken, then you also have to stand very closely with other people. So think of the MRT as your solvent. Okay, the MRT is your solvent. And then the people, they are your particles. Okay, then the MRT is the solvent. So which one has more particles per unit volume? Is it Non-peak hour or peak hour? Okay, can you guys comment down below? Which one has more particles per unit volume? More particles per unit volume. Okay, is it A, which is non-peak hour, or is it B, which is peak hour? Okay, yes, Fave said peak hour. Okay, what about the rest? Is it A or B? Non-peak hour or peak hour? Which one has more people in the same volume? Are you funny? C. Okay, it's B, peak hour. So that is what concentration means. Okay, if you increase concentration, it means that the number of particles per unit volume also increase. So when we want to explain, that's the first thing we'll say. Number of reacting particles per unit volume increases. Okay, then how does this lead to rate of reaction increasing, right? Rate of reaction increasing is when we have more effective collisions. Think about it. When you are in a squeezy MRT, right, versus when you are in a MRT with so little people, which one will you collide with more people? The peak hour MRT, right? So when you have more particles in the same volume, you will have more collisions, right? You'll collide with more people. So when you collide with more people, you actually have more effective collisions also. Okay, let me explain to you why. Okay, let's say we have two reactions, right? The first reaction, you have 1,000 collisions. Okay, then the second reaction, you have 2,000 collisions. Okay, then out of the 2,000, 1,000 is effective. Out of the 1,000, 500 is effective. Okay, so you see how I link it or not? 1,000 versus 2,000 collisions, which one got more effective collisions? Of course, it's the one with 2,000 collisions. So this is how I link it. When I have more collisions, right, I also have more effective collisions, right? The frequency of effective collisions also increase. Okay? Because when I have 2,000 collisions, I have 1,000 effective collisions. But when I have 1,000 collisions, I only have 500 effective. So they're also directly proportional. The more collisions you have, the more chance you will have more effective collisions also. Okay, so that's the linking. And once you say you have more effective collisions, higher frequency of effective collisions, that leads to faster rate of reaction. Okay, so from the start, concentration increase, right? You have more particles per unit volume. So you have more collisions. The particles have more collisions. So the frequency of effective collisions increase, and therefore rate of reaction increase. Okay, so let's look at the first question. Dilute hydrochloric acid is reacted with 1.2 grams of magnesium ribbon at room temperature in two experiments. Okay, in experiment 1, this volume, 100 cm cube, 1 mole per dm cube of hydrochloric acid is used. Okay, then in experiment 2, 50 cm cube and 2 mole per dm cube of hydrochloric acid is used. So the volume of hydrogen is given off, that is given off is plotted against time. Okay. So which graph is correct? Okay, first let's find the number of moles of this, okay? Because we need to make sure that is the, okay, actually, okay, we don't need. First thing we look at is the concentration, okay? When you look at graph, right, there are two things that you need to notice. One is the gradient. Two is the volume of product form. Okay, who can tell me what gradient represents? What does a gradient in a volume time graph represent in rate of reaction? What does gradient tell you? So when you measure the gradient, correct, it tells you the speed, right? It tells you the rate of reaction. Okay, so the steeper the gradient, if it's more steep, the rate of reaction is higher. Okay. So how do you know whether it's steep or not? Just imagine you are a person climbing a hill. Okay, pretend you are a person climbing a hill. Then just think which hill is harder to climb. Of course, number one is harder to climb, right? Because it's more angled upwards. So if it's more harder to climb, it is the steeper graph. Okay, so for A, number one is the steeper graph. Okay, but let's look at which one should be steeper. So the factor that affects rate of reaction here is concentration. Okay, concentration in mole per dm cube. So obviously experiment 2 has higher concentration, right? Okay, so we know that it has a higher or faster rate of reaction. So experiment 2 should be the steeper graph. Okay, experiment 2 should have a steeper graph. So I can immediately eliminate A and B, right? Okay, because A, number 1 is steeper, and B, number 1 is steeper also. So this is wrong. Okay, then what's the second thing we have to look out for? Volume of product form, right? How do we tell the volume of product form? Very simple. We find the number of moles. We find the number of moles of your limiting reagent. Okay, so if you actually do calculations, right, you find the mole of magnesium, you find the mole of hydrochloric acid, you'll realize that hydrochloric acid is the limiting reagent. Okay, or at least it's equal. So for this, we'll just skip that. We'll just go straight into finding the moles of hydrochloric acid. Okay, because it's the one that has the concentration. So how do you find the mole? Okay, let's start with experiment 1. Okay, for this, we are given volume and concentration of a solution. So mole equals to volume times concentration. Okay, the volume is 100. But remember, we have to convert from cm cube to dm cube. So 100 over 1000 times 1. Okay, 100 over 1000 times 1. Okay, so experiment 1, the number of moles is 0.1. Then for experiment 2, it is 50 over 1000 times 2, which will also give me 0.1 mole. Okay, so what I'll do now is I compare the number of moles. Since the number of moles is the same, that means the volume of your product form, the volume of your gas hydrogen form will also be the same. Okay, it will also be the same. So your final volume should be the same. Your answer is D. Okay, this one, the final volume is not the same, so it's wrong. Okay, so remember your exams like to test you on graph also. So for the graph, take note of two things. One is the gradient, which is the rate of reaction, and second is the volume of product form, which can be found by finding the number of moles of your limiting reactant. Okay. All right, any questions? Just let me know in the in-call messages. Okay, I'll be moving on to the second factor now. Okay, so you understand concentration already. Okay, second factor, pressure. So pressure is very similar to concentration. Similar to concentration. Okay, but the difference between concentration and pressure is that concentration is for your solutions. Okay, for your aqueous solutions, like sodium chloride solution, hydrochloric acid solution, but pressure, right, is only for gases. Okay, hydrogen, oxygen, gases only. So you have to take note, you cannot use pressure for solutions, you only can use pressure for gases. Okay, so let me draw two boxes and then I want you guys to compare. Okay, then the second box. Okay, which one has higher pressure? Box 1 or 2? Which one has higher pressure? Please comment down. Which one has higher pressure? Okay, Kana said 2. What about the rest? Which one has higher pressure? Okay, so 2 has higher pressure, and this is why, okay? Pressure, right, you can think of it as similar to concentration, number of particles over unit volume, okay? In box 1 and 2, the volume is the same, okay? But in box 2, the particles, there are 12 particles, okay? So the number of particles increase in box 2. So the pressure is higher. Okay, but we cannot use number of particles per unit volume to explain for pressure. Okay, for pressure we will use the distance between the particles. Okay. So if we talk about distance between particles, right? Box 2, you'll realize that the distance is closer. Okay, then box 1, the distance between the particles is further. Okay. So now we can link pressure to distance between the particles. Okay. If the pressure of my gas reactants increase, right? Okay. My reacting particles become closer together. Okay. My reacting particles become closer together. So what does that mean? If my particles are closer, there are more chances that they will collide, right? Okay. But think about this versus this. Which one will have more collisions? Of course, box 2, right? Okay, box 2 will have more collisions. So the particles are closer together. There will be more collisions. Okay, and just now we learned that if there's more collisions, there's also more effective collisions. So frequency of effective collisions increases, and therefore rate of reaction increases. Okay, but pressure is not only changed by increasing the number of particles, right? We can also decrease the volume, but the same thing will happen. Okay, let me show you. I draw another 2 boxes. Okay, as you can see, box 2, right? I decrease the volume, but the number of particles is still the same. Okay, but you realize that the particles in box 2, they are closer. Okay, the particles are closer compared to box 1. So same thing, we will use particles come closer together. If the pressure increase, the particles come closer together, and then there will be higher chances of collisions. So more collisions. More collisions means frequency of effective collisions will increase. Okay, think about it. If you keep colliding, right, of course, there will be higher chances that you will have more effective collisions. Okay, and effective collisions is what causes a reaction to happen. So if you have more of those, you have a higher rate of reaction. Okay, so that's pressure. That's how we explain pressure that affects rate of reaction. Okay, by the way, you only explain like that, right? Usually when the question asks you to use collision theory. Okay, usually. Okay, now for question 2. Okay, sorry, wait, let me plug in my laptop charger. Okay, for question 2, since this is a true-false statement of question, I want you guys to tell me your answers. Okay, we will go from A to E, okay? Okay, so study the following statements. Answer each statement by using the letter T for true statement and F for false statement. Okay, so the first statement, the effect of pressure on the rate of reaction is greater in a chemical reaction that involves solids and liquids only. Okay, true or false? Okay, Sharinte said false. Okay, but if you guys are wondering, why is it false? Think about your solids and liquids, right? Go back to chapter 2. Or is it chapter 1? I forgot already. I think chapter 2, kinetic particle theory, right? Solids, the particles are very closely packed in an orderly arrangement, right? This is solid. Then liquid, they are also very closely packed, but slightly irregular arrangement. Okay? But in both of these scenarios, right? Yes, J asks, so volume decrease, pressure increase. That's correct. Okay, in both of these scenarios, the particles are very close together. So if the particles are very close together, then if I increase pressure, right, they can't really get that much closer. So it doesn't really affect so much. Okay. So if I increase pressure, the pressure doesn't really increase a lot. because the particles are already so close together. Okay, that's why, right? For pressure, we only talk about gases. Okay, remember, pressure only talk about gases. For solids and liquids, it doesn't really affect it that much. Okay, statement B, sorry. A higher pressure is achieved when the volume of a fixed amount of particles is reduced. True or false? True for 2, yes. Okay. Okay, J also asked the same question, which is if volume decrease, pressure increase? Yes. Okay, volume decrease, and then if the number of particles stays the same, the pressure will increase. Okay, like this example here, the blue example, right? There's the same number of particles, but for box 2, the volume decrease, so the pressure increase. Okay, C, the gaseous particles are packed together closer at a lower pressure than higher pressure. True or false? Okay, good. False for 3. Okay, I want other people to participate as well. Okay, so if you're packed closer, right? If particles are packed closer, the pressure will be higher. Okay, not lower. Lower is wrong. Okay, D. At high pressure, the number of collisions increases that leads to more effective collisions. This causes the speed of reaction to be faster. Yes, D is true. Okay, good. YW. So high pressure, the particles are closer together. So there will be more collisions. And more collisions means that more effective collisions. Okay, more effective collisions, faster speed of reaction. Okay, speed of reaction, rate of reaction is the same thing, by the way. True. E, when the number of particles in a given volume decreases, the pressure becomes lower. True or false? Yes, true also. Okay, good job. So this is the first example, box 1 and box 2. When I have less particles, they are further away from each other, so the pressure is lower. Okay, good. So that is the second factor. We are moving quite well. Okay, 3 more factors to go. Third factor is particle size of solid reactants. Okay, so we need to understand this relationship here. The smaller the particle size, the more the exposed surface area. Okay, by the way, particle size is only for solids. So far concentration is for solutions, pressure is for gases, particle size is for solid. Okay, but why smaller particle size, more exposed surface area? I'll give you a very simple example. So let me draw this ice cube. Okay, this nice ice cube. Let's say one side is 2 cm. What's the last two answer? Both true? Yes, both true. Yeah, both true. Okay, make sure you understand why it's true also. Wow, how to draw so nice. Nice, man. Okay, surface area to volume ratio, you can say that also, but in our syllabus, we can just say exposed surface area. Okay, so let's look at this. Let's say this ice cube is 2 cm each side. Okay, so the area of one side is 2 cm times 2 cm. Okay, then how many sides does a cube have? Come on, anyone? How many sides does a cube have? How many sides does a cube have? 6, yes. Okay, so 4 cm cube times 6, 24 cm cube. Okay, so this is the surface area for your ice cube. Now let's say I crush this ice cube into 8 pieces. Okay, I crush it into 8 pieces. So this, now once one piece is like that, then I have 8 of these. Okay, I have 8 of these. Okay, now of course, one side is 1 cm. Okay, so the surface area of 1 is 1 times 1. And then you guys say there's 6 sides. So there's 6. Surface area of 1 is 6 cm cube. Cm squared, sorry. But now I have 8 of these because I cut into 8 small pieces. So my total surface area now is 48 cm cube. Do you notice it's actually double? Okay, but double is not the point now. The point is that it is more than the bigger particle size, right? When I cut this particle size into 8 pieces, the total exposed surface area is more. Okay, so smaller particle size, larger exposed surface area. Then if there's more exposed surface area, right, there's more area for collisions. Right, there's more area for collisions. So you have more collisions. And then more collisions, again, same thing, right? More frequency of effective collisions. Therefore, rate of reaction increase. Yeah. Then of course it's the same thing for the opposite lah. So if the particle size is bigger, exposed surface area is lesser, there is less collisions, less effective collisions, and slower rate of reaction. So you just need to know the beginning, and then you can link it all the way to the end. Okay, let's try question 3. Again, don't worry if you cannot copy. I will send the inkings into the Telegram channel. Or you can WhatsApp me directly if you're not in the Telegram channel. Okay, question 3. 3 experiments are carried out to investigate the factors affecting rate of reaction as shown in the table below. Okay, so later I'll go through this table. The graph below shows the results of these 3 experiments. Explain why the curve of experiment B has a steeper gradient than that of experiment A. Can you say that there are 8 small cubes versus 1 large cube? So there are more particles and hence higher collision rate. Don't use more particles, okay? Don't use the word more particles. Exam, right? I mean, in chemistry, right, they are looking for keywords. So the keyword here is your particle size is smaller, therefore your surface area increase. Okay, use the words particle size and surface area. Don't use more particles for this factor. Okay, yeah. Because it's more surface area, that's why there is more collisions. Okay. Okay, back to this question. Explain why curve of B has a steeper gradient. So again, steeper gradient means faster rate of reaction. Okay, why do we say, but the numbers increases, is it? But the numbers increases it. Okay, it's actually the same. It's the same particle, right? It's the same particle. It's the same thing. It's just that we have more exposed surface area now. That's why the more exposed surface area, particles can collide with the more exposed surface area, right? So there are more collisions. Usually, if you want to say more particles, right, we talk about it using concentration. Okay, concentration increase, then number of particles per unit volume increase. Okay, but we never only say that particles increase. Okay? Okay, so remember for particle size, just talk about exposed surface area. Okay, explain why the curve has steeper gradient. So steeper gradient means faster rate of reaction, right? And why does it have faster rate of reaction? Because B uses calcium carbonate powder and A uses calcium carbonate lump. Okay, so powder has a smaller particle size compared to lumps lah. So calcium carbonate powder in B has smaller particle size than the calcium carbonate lump in A. Okay, so smaller particle size means there is more exposed surface area. So the total exposed surface area of CaCO3 powder is greater. leading to a faster rate of reaction. Okay, that's why faster rate of reaction, steeper gradient. Okay, so you can say hence a steeper gradient. Okay, keywords here, smaller particle size, total surface area is greater, therefore faster rate of reaction. Okay, by the way, lumps, right? Lumps are like that. Then powder is like that. So you can see the particle size is completely different. Powder is much smaller particle size. Okay, then we don't have to talk about the concentration because all the concentration is the same. Okay. And by the way, in this question, we don't talk about the collisions because the question never really asks about using collision theory. And even if they didn't, right, sometimes you can tell whether you need to add in or not. So if the question is like very short question, then you probably don't have to add in. But if it's a very long question, you probably have to talk about collision theory. Or if you write about a collision, they won't deduct marks either. Yeah. Okay, so usually exam question, they'll be more specific. If they really want you to talk about the collision, they'll say this in terms of collision theory. Okay, so not to worry too much about that. Yeah, but for part 3, we'll definitely use collision theory. Okay, so I can just write using collision theory. Hey, wait, part 3. No, actually, part 3 don't need. Sorry. Part 3 don't need. Okay, let's look at part 2. Sketch on the same graph the curve for experiment 3. Okay, remember graph, what are the two things that I'm looking for? Can anyone tell me? What must I focus on in a graph? The first one starts with G. What is the first one? What's the first thing that I should look out for in the graph? If I want to sketch or if I want to study it. Yes, gradient. Good job. Okay, then what's the second thing? It'll be the volume of your gas produced, okay, or product produced. Okay, so for gradient, we use the rate of reaction. 930, yeah, 930. So for volume, right, we use mole. Mole of your limiting reactant. So for experiment C, we have to compare with another thing that is quite related. So we look at C, right? We can compare it to B as well. B and C, they have the same particle size, which is powder, and they also have the same concentration, right, which is 1 mole per dm cube. So what does that tell us? They will have the same initial rate of reaction. So when I'm drawing my graph, make sure I line up exactly with B at the start. Understand? Okay, must have the same gradient. Same initial gradient. Okay, because rate of reaction also decreases as you go on. Okay, so gradient we know already is the same at the start. But what about volume of gas produced? We have to find the number of moles of your limiting reactant. Okay, question for you guys. Which one is the limiting reactant here? Is it calcium carbonate or is it HCl? Which one is limiting? Yes, HCl. Good. Okay, because they already say that calcium carbonate is excess. So quite obvious that the other one is limiting. So since HCl is limiting, let's find the number of moles. Okay, so this one will be 40 over 1000 times 1, which is 0.04 moles. Okay, this one is 20 over 1000 times 1, 0.02 mole. Okay, so we are comparing C with B, right? You realize that C has half the number of moles as B, right? The HCl has half. It's half the amount. So the volume of carbon dioxide produced should also be half. Understand? Okay, so the mole of your limiting reactant is directly related to the volume of your product form. So now we can draw our graph. Okay, my graph won't be the best because I'm drawing on the iPad. But you can use the curve ruler if you like to. Okay, draw until here. Draw halfway, then after that draw a straight line. Yeah, something like that. Then you label experiment C. Okay, make sure the initial gradient is same as B. Okay, how do I? Let me use a different color. Same gradient as B. And then make sure the volume of product form is half compared to B. Okay, so this is B and this is C. Is half. Okay, initial rate of reaction is the same when you compare C and B because they both use calcium carbonate powder, okay, which has the same particle size. But that's not all, right? What's the other factor that affects rate of reaction? Here is your concentration, right? 1 mole per dm cube. The concentration of HCl is also the same at 1 mole per dm cube. Okay, so this will explain why it has the same gradient, the same initial speed of reaction. Okay, but however, why is the volume of carbon dioxide formed half? Because the number of moles of HCl is half compared to B, right? Half in C compared to B. Thus, the total volume of carbon dioxide is also half the amount. Okay, keyword initial rate of reaction is the same because they both use the same particle size, which is calcium carbonate powder. And then concentration is also the same, okay, at 1 mole per dm cube. But number of moles is half in C compared to B. Number of moles of HCl. Okay, so total volume of CO2 is also half. Okay, let's move on to the next one. Temperature of reacting system. Okay, I say reacting system because now, or temperature, right? It can affect all types of reactions, reactants, right? Solid, liquid, gas, aqueous, temperature can affect all of those. Okay, so temperature, right? There are two explanations to this. Like when you want to explain why temperature increase rate of reaction using collision theory, you have to give two explanations. Okay, and it's very difficult to memorize the answer. So I'll give you a simple analogy to, not analogy, you guys just watch these videos, okay? I'm gonna play these two videos, and then you guys are gonna ask yourself two questions. Okay, two questions. There'll be people in the video. So I want you to ask, how are the people moving? Are they moving really slow? Or are they moving really fast, very rush? Okay, so is it slow and very calm, or is it fast and very rush? That's the first question. Second question is, because this whole chapter is on colliding, right? Particles colliding. How often are the people colliding with each other? Okay, so it can be like never, or not often, or very often. Okay, so I want you guys to ask these two questions, and then later, after I play the video, tell me your answers. Can? Okay, let me play the first video. How are the people moving, and how often are they colliding with each other? By the way, it's only 15 seconds long. It's a very quick video. Okay. Okay, so first question, how are the people moving? Is it slow and calm, or is it very fast and rush? Slow or fast? Quite slow, okay. What about other people? What do you think? Are they moving very slow or fast? Slow and furious. I wouldn't say they are furious. I think they're actually quite calm. Okay, slow. Okay, then how often are the people colliding with each other? Are they never colliding, or not often, or they are colliding very often? Never, yes. Okay, never colliding. Okay. So this is an example of when the temperature is low. Okay, so when the temperature is low, right? Yeah. The particles, now your people become your particles. The particles move slowly. Okay, and then the frequency of collisions is very low. Okay, in fact, they never even collide with each other. Now I want you guys to watch the second video and again ask yourself the same two questions. How are the people moving, slow or fast? And how often are the people colliding with each other? Okay, comments. How are the people moving? Are they very slow and calm, or are they are they rushing? How are the people moving? Fast and furious. Nice. Okay, and how often are they colliding with each other? Yeah, always colliding, right? Very often. Okay, so this is what happens when there is high temperature. When you raise the temperature, YW Lee said high frequency of collision. That is correct. Okay, so the first thing is that now the people become particles. Okay, so the particles are your people. So the particles, they move very fast. Okay, and then you see they keep colliding with each other, right? So the collisions, the frequency of collisions is very high. Okay, now let's see how do we explain in terms of collision theory. So when I increase the temperature, the particles gain kinetic energy. Okay, you need to understand that temperature is directly correlated to kinetic energy. So if you increase the temperature, the particles will have more kinetic energy. So they move faster, and just like what YW said, there is a higher frequency of collision. Okay, when they move faster, they collide more frequently. But that's not the only reason. There's another factor that actually causes the reaction to rate of reaction to be faster. Think about it. If the kinetic energy of the particles increase, that means each particle, right? There is more energy. There is more energy within each particle. So when the particles collide with one another, they collide with more energy also. Okay? So when they collide with more energy, there's a higher chance that those particles will also meet the activation energy, which is the second part of your collision theory, right? When your particles collide and they meet the activation energy, there will be a reaction. So the second part is because now your particles have more kinetic energy, more particles will have energy greater than or equal to the activation energy. Okay, so the frequency of effective collisions increase, and therefore rate of reaction increase. Okay, if you're not so sure what this, if you're still not sure what this means, right? Let me give you an example. Let's say, right, the activation energy, let's say the activation energy is 500 kilojoules. Then when the temperature was 25 degrees, I have 100 particles. I have 100 particles colliding at 400 kilojoules of energy. But when I increase the temperature to, let's say, 50 degrees, these same 100 particles, right, now they collide at 600 kilojoules. Okay, so before that, these collisions, they were ineffective, right? Remember, ineffective collisions, they never meet the activation energy. But now, after the temperature increase, more particles meet the activation energy. And if there's more particles meeting the activation energy, it's the same thing as saying there's more effective collisions. Okay, so that is the second reason. First reason is they move faster, then they collide more. Second reason is there will be more particles meeting the activation energy. So they will have energy equal to the activation energy or greater than the activation energy. Okay, so you have to state both reasons. Okay, so let's look at question 4. A student investigated the rate of reaction when dilute acid reacts with excess solid copper 2 carbonate. Okay, he used the same volume of acid each time. Okay, same volume of acid. He measured the time taken to collect 10 cm cube of gas at room temperature and pressure. And he also measured total volume of gas at the end. Okay, so I have concentration. Concentration will affect rate of reaction. Okay. So just keep in mind. Okay, let's look at part one. The student carried out 3 experiments using acid at room temperature and 1 experiment used at higher temperature. So which experiment was carried out at a higher temperature will be the one where it has the shortest time taken, right, to collect the gas. Because the time taken to collect 10 cm3 of gas, that will be the rate of reaction. Okay, but we have to make sure, right, if we are increasing temperature, the rest of the factors affecting rate of reaction has to be constant. So I can only use this, and this. This one is not constant. I mean, this one is not the same concentration. Okay, so I'm going to compare 1, 3, and 4, and your answer will be this one. Right? 7 seconds is the shortest time. So experiment 3. Okay, explain your answer. Comparing 1, 3, and 4, which used the same concentration. Okay, when we use the same concentration, I don't say the rate of reaction is the fastest. I use exactly what they give me in the table. Okay, so the time taken to collect 10 cm3 of gas. Okay, the time taken to collect 10 cm3 of gas, this is actually rate of reaction. Okay, so you don't always have to use rate of reaction. Sometimes you have to use what the question gives you. So time taken to collect gas, that is a form of measuring rate of reaction. And the shortest time is the fastest rate. Explain in terms of collisions between reacting particles, why higher temperature affects the rate of reaction. Okay, so this one is 3 marks. Temperature is by far the hardest one to explain, right? Because there are 2 explanations. So firstly, when temperature increases, kinetic energy increases. Okay, just like the video just now you saw in the second video, you can see like the kinetic energy of the people increasing, right? So when temperature increases, the kinetic energy of reacting particles increases, right? So it means they move faster and collide more frequently. Okay, this is the first reason. But the second reason that makes the reaction faster is that more particles will have more energy, right? So more particles will have energy that is greater than or equal to the activation energy. So more particles, when they collide, right, they are actually meeting the activation energy and they will have more effective collisions. Okay, I'll give you all like 1 minute to copy this, then I'll move on to the last factor. Okay, then after the last factor, we can play the Kahoot quiz. Okay, back to the question, right? Experiment 2, why can't you halve? So experiment 2 is 1 mole per dm cube, and the timing is 6 seconds. Okay, if I were to halve, it does not mean that this one is 12 seconds. Okay, it's not directly proportional. And even if it means that, right, that just also proves that the 7 seconds is the faster one. Yeah, but it does not mean this. This is wrong. Okay, let's move on to the last factor, which is catalyst. Okay, first we need to understand what does a catalyst do. A catalyst provides an alternative pathway with lower activation energy. Okay, so if there's lower activation energy, frequency of effective collisions increase. Okay, let me give you these examples. Okay, when we are comparing activation energy, right? Why does lower activation energy means that there's more frequency of effective collisions? Just look at this example here. Let's say, right, 100 particles collide at 400 kilojoules of energy, and then another 100 particles collide at 300 kilojoules of energy. If my activation energy was 500 kilojoules, how many effective collisions do I have? Can someone give me the number? How many effective collisions do I have if activation energy is 500? Okay, so for number 1 versus number 2. Yes, Hokana says 0, correct? Because none of the energy meets the activation energy. Okay. What about for the second one? The same 100 particles collide at 400 kilojoules of energy, and then another 100 collide at 300 kilojoules of energy. How many effective collisions do I have? Okay, it is not 100. As long as it is equal to the activation energy or greater, there will be a reaction. Okay, good. 200. Yes. Okay, so both of these meet the activation energy. So this proves the point that if my activation energy is lower, if I have 300 instead of 500, then I will have more effective collisions. Okay, so that's how I link. Lower activation energy, more effective collisions, faster rate of reaction. Okay. So examples of catalysts, your transition metals like platinum, nickel, and iron. So transition metals, they are in the middle of the periodic table from like group 3 to 12. Okay. Okay, transition metal oxides, manganese 4 oxide, vanadium 5 oxide, and also enzymes. Okay, these are all examples of catalysts. Okay, for now, you don't have to memorize this. Okay, climbing a hill energy. Imagine you're climbing a hill, right? Then suddenly, all of a sudden, you have a shortcut. Okay, so which hill is easier to climb now? A or B? Which hill is easier to climb? B, right? Yeah, B is easier to climb. Okay, now think of it as this is the activation energy. B has lower activation energy. So it is easier for the particles to meet the activation energy. It is easier to climb the hill. So since it's easier to climb the hill, in terms of this, there is more effective collisions. Okay. So if I can reach the end faster, it means that faster rate of reaction. So catalyst, the explanation is quite straightforward. Okay, so we can practice our explanation skills in question 5. Without the catalyst, the reaction between oxygen and carbon monoxide is very slow. Explain in terms of collisions and energy why using a palladium catalyst increases the rate of this reaction. Okay, actually, after saying lower activation energy, there's one more thing we have to say, which is more particles can have energy greater than or equal to the activation energy. Okay, let's specify the particles. So more oxygen and carbon monoxide particles. They will have energy greater than or equal to activation energy. Okay, then the same linking. So the frequency of effective collisions increases and then rate of reaction increases. Okay, once you all are done copying, you all can go to kahoot.it already. Yeah. So what must occur to reactant particles for a chemical reaction to happen? They must not only collide, right? They must collide with enough energy. Okay, remember there are two parts to collision theory. They must collide and they must collide with enough energy, which is the activation energy. Okay. Okay, good job. Okay, nice. Everyone got it correct. So best describes ineffective collision, collision that does not result in a chemical reaction. Good job, everyone. Yes, collision with enough energy where you can form products. That means a chemical reaction has happened. What does frequency of effective collisions mean? Okay, so for those of you who put the total number of collisions between all particles per unit time, that one is only collisions in general. That means collisions in general, they include effective collisions and they also include ineffective collisions. But here we are talking about effective only. So effective only, it has to successfully form products, has to have a successful chemical reaction. If you say all particles, if you say collisions in general, you are talking about both effective and ineffective. Okay, so green is your answer. Okay, YW has taken the lead. Good job, everyone. What happens when concentration of the solution increases? There are more collisions per second. Okay, basically higher frequency of collisions. So pressure, right, is always about how close the particles are together. So the closer the particles are together, the higher the pressure. If you say particles move faster, this is not true. All the particles, as long as you never increase the temperature, as long as the temperature is the same, the kinetic energy is also the same. So they move at the same speed. Okay. Okay, Rainian is back at the top. Oh, all 7 of you got it correct. So why does smaller particle size of solid reactors increase rate of reaction? Because there's more exposed surface area, okay, for collisions. Okay, nice. Okay, why does increasing temperature increase the frequency of effective collisions between particles? Particles move faster and collide more often, correct. More particles have greater energy greater than or equal to activation energy, also correct. Okay, so both are correct reasons. If you only read until blue and then you click your answer, and then you never read the third option, then yeah, you are wrong. But red and blue is both correct. So yellow is the answer. Okay, both are correct reasons. Okay, wow, Emmeline has jumped to second. What does a catalyst do? Provides an alternative pathway with lower activation energy. Good job, everyone. Which setup has the highest collision frequency? Okay, so for this, there are two factors that affect rate of reaction. One is your concentration, mole per dm cube. The other one is your temperature. So highest collision frequency will be highest temperature and highest concentration. And that will be rate. Okay, 3 mole per dm cube and 25 degrees Celsius. Okay, nice. Which setup will produce the gas in the shortest time? Okay, now we have 3 different factors. One is particle size, concentration, and temperature. So produce the gas in the shortest time means fastest rate of reaction. So you need smallest particle size, highest concentration, and highest temperature. Powder will have the smallest, particle size, and then 2 is the highest concentration, and 25 degrees. Okay, so blue is your answer. Red is wrong because chips is not as fine, not as small as powder. Okay, let's see the top 3. Okay, Zhou Yiran, third place, good job. YW second. And Rainian is first. Okay, good job. Now I'll share my screen back to the PDF. Okay, now right, I want all of you to think of one thing that you improved the most today. And then once you thought of it, write it down in the in-call messages. Write it down in the chat. Okay, everyone has to share at least one thing. What was one concept or one part that you benefited the most today, that you improved the most? MRT analogy, ice cube analogy, box analogy. Or you remember all the analogy? Molten temperature video. Okay, good. Yeah, because temperature, right? That one is hard to explain with just words. So I try to use the video. Examples for each factors. Okay, nice. You like the IN video. Okay, so if you guys are thinking of joining our regular weekly classes, right? Don't wait any longer. Because first reason, most students, they have this hope that chemistry is going to get better. You know, you'll figure it out when it's closer to O levels. But here's a personal story, right? When I was in Sec 4, throughout the year, for physics, my grades just got worse and worse. So from B4 to C6 to even lower. And then when I joined tuition, I realized that firstly, it was the content foundation. It was very bad. And I also don't know how to apply the content into the answer. Right? For chemistry, it's even harder because chemistry is not a topic where you can just copy and paste answer. You have to understand, then you have to know which concept to apply. Okay, so it really helped me when I got the support I wanted. Then the next reason is every lesson we jam pack with so much content. Okay, we go through a lot of questions, we go through a lot of analogies. So the later you join, the more you're missing out on. Okay, and the third reason is later in the year, if we hit max capacity, we won't accept any more students. Yeah. So join before that happens. And yeah, here is what you get as a student. You can take screenshots, show your parents, all this. Okay. All right. So I'm actually planning to give away the common structured questions for rate of reaction. Okay, I'll just send it to you if you fill up this feedback form. Okay, so can you scan this QR code and fill up the feedback form? Then for those people who fill up the feedback form, I will send you these common structured questions for rate of reaction. It has all the sciences, not sciences, what am I saying? It has all the answers. Okay, it will show you the common questions that the teacher asks or the exam like to ask, and then the answers. Sure, do you know who's Zhou Yiran? I know it's a person. Sure, how to scan? Okay, you don't know how to scan, then you type this. Okay, if you cannot scan, if you're using your phone, then you can just type this link, tinyurl.com/lch feedback. Okay, then if you are interested for our weekly lessons, you can just WhatsApp me that you're interested, or you can sign up directly here. Okay, tinyurl.com/signuplch.